formation and the transition to the higher bands are essentially sort of, cancel each other out and then give large contributions to the effective hopping. Can this be controlled, or is it, you showed sort of this behavior near the Feshbacher resonance where there's some peaks, or can this be understood quantitatively, or is it just sort of in a way on a qualitative level?
It's at least semi-quantitative. We had, especially for the broader resonance, we had enough magnetic field control that instead of looking for, variation, in other words, we could really control the super exchange by very, very fine-tuning into those laser-induced resonances. So in other words, we had an opportunity to control spin exchange parameters, not via the atomic physics resonance, but by exploiting the possibility of creating molecules on a site. It's really sort of funny. I couldn't believe it first. You have sort of your atoms hopping around. And then if atoms are aligned with spin, they have a different super exchange interaction than if the spins are different and such. And what we found is that the whole spin dynamics was controlled by when two atoms with a spin in the z direction came close, they started to tunnel over, form a temporary molecule, and tunnel back. And this process of tunneling over, forming a molecule, and tunneling back, this process determined how the macroscopic spin system performed. But it is controllable. I'm not sure if I would necessarily suggest that as the best way to control it, but it gives you clearly, if we had reason not to change scattering lengths over a large magnetic field range, here we could pretty much get all anisotropies within a Gauss or two by using these narrow resonances. It is a possible tool, but at least it's something people should pay attention to.
Questions?
Maybe the conclusion is the following. You always have to be aware what you are doing. And if you vary the scattering lengths, whenever you have a scattering length A, you have a bound state with a binding energy 1 over a square. There is no way to change scattering lengths in atoms without playing also with the bound state. And the bound state is there whether you like it or not. And here we showed how this bound state of two atoms suddenly, jumps out and plays a very, very strong role. But it's always an ingredient. We cannot suppress it. And if it's there, we may as well utilize it for something. But maybe on a pragmatic side, those new resonances of molecular bound states are only experimentally relevant and can be experimentally used when the binding energy of the molecule is relatively small. Because you want the binding energy of the molecules to be on the order of the band structure. And that only happens close to a Feshbach resonance. So in other words, if you have no Feshbach resonance at all in your system, you are screwed. This doesn't help you. This is just creating satellite Feshbach resonances, additional Feshbach resonance close to the ordinary Feshbach resonance.
Yeah, I just had a remark. So you were a bit negative about the chances of cold atoms to produce high precision data which cannot be done by experiments. But actually we have some known examples where cold atoms produced pretty accurate data which to some extent have not yet been achieved by theory, right? So for example, the equation of state of the unitary gas and the superfluid phase, that's not yet done. The experiments are ahead of theory, or for the polarized Fermi gas, or also for the contact in the superfluid phase. So I would hope that there will be more of these kind of things also in the future.
I do agree. I mean, I'm making some provocative statements, and not everything I've said should be completely generalized. I just want to say is, in my experience, I realize the limitation. I realize how important it is to have the theoretical input. And I would say, where has really experiment provided precision numbers which are leading the theory? We have the example of the unitary Fermi gas, but I don't think we have many more examples. And also, I mean, if you follow the history of the unitary Fermi gas, there was a head-to-head race between maybe Martin Zwirlein and Wilhelm's calculations and the calculations of the Amherst group. And just as a case in point, I know when Martin had the final precision, there was a small discrepancy to the latest calculation from Prokofiev and Svistunov. And I think then they realized that also they had 100 Gauss-Feschbar resonance, they were possibly 1 Gauss away. And so the scattering length was not infinite. And then they had to put a small correction in, and then they got agreement. So even at their ultimate level of precision, they would have possibly made a mistake without the input from theory. So in that sense, if the experiment had produced a number which is 10 times more accurate than any theory, it would be a wonderful accomplishment, but I would not have taken those numbers at face value. Because there's...
But then they extended the measurements, experimental measurements to the superfluid phase, where we did not have the accurate theory, the control theory. So
in contrast to the normal state.
yes.
Yeah, okay. The equation of state was really taken outside the range where it can...
Yeah, but this couldn't be known.
No, I agree.
But it's not. It seems to me notable that all the examples you quoted are without a lattice. Without a lattice. And it seems to me that indeed in the trap there are the cases you quoted in which to some extent experiments are ahead of theory, of computational methods and theory. But in the lattice, it's a different game, right? So there are intrinsic experimental difficulties of cooling in the lattice that, and I think that's what Wolfgang was pointing out.
I mean, it depends. I would say, yes, we are all very, very proud of the unitary Fermi gas. The experiments have really introduced, the concept of precision many-body physics, and it has gone very well. And this is, but for me, I would love to see more examples of that, but I do see, especially in more complicated systems, additional difficulties. But, yeah.
But interestingly, I mean, this was a wonderful talk, but interestingly, you didn't mention transport as a possible place where the experiments then can tell us things that theory cannot. So is that because, you think this is not an interesting direction, or is that because you didn't have enough time, or what?
Well, I wasn't sure if I can say something very intelligent about it. I mean, the transport requires some inhomogeneity. You have to prepare an inhomogeneous system, see it relax and all that. And that, of course, opens the door to how well can you control things. So, but I think, especially in 2 dimensions with a microscope, we should be able, with projection methods, to prepare very, very well an initial state and then observe transport. So I think there is a big opportunity. And when we talk about quantum simulations and comparison with calculational efforts, I mean, you've told me that the bar is much lower for transport because it's much harder for the theory to do transport. So maybe that's a place where the experiment can lead the theory.
Yeah,
but
that's also
I stand by my statement, but it's partially philosophical outlook, I think if experiments would go far ahead from theory, I would not trust the experiments anymore. So maybe it's just the interesting situation with the unitary Fermi gas that the experiment is just one step ahead of theory, where the experiment is still validated sufficiently that we can trust the experiment. But if an experiment would go far away from theory, I think we are losing a little bit the element which is so important in the experiment, that we can also validate what we are doing. We always, I mean, absolute measurements are really difficult, but if you have a unitary Fermi gas, but you can just switch back and forth between an ideal Fermi gas and a unitary Fermi gas, you can do a lot of referencing between a situation which you know and what you don't know, and this takes a lot of the calibration problems out of. So anyway, we'll see. I mean, of course, I hope as an experimentalist that we go far ahead of, you know, theory, but I have my doubts, but I'm looking at the future with a lot of excitement.
So then I'll just So any more questions? Or shall we close? I think Ivan would like to say a few words then. Let's thank again Wolfgang and Sylvain for the nice lectures.